Hi students, today I am going to deal the topic interferometers from the chapter analyzers. Today I am going to deal the topic interferometers from the chapter analyzers. Learning objectives. Upon completion of this presentation, you will be able to understand the concepts of interference, constructive and destructive interference, the interferometer, the principle of interferometer, types of interferometers, components of interferometers, construction and working of Michelson's interferometer, and applications of interferometers. Upon completion of this presentation, you will be able to understand the concept of interference, constructive interference and destructive interference, interferometer, the principle of interferometer, types of interferometers, components of interferometer, construction and working of Michelson's interferometer, application of interferometer. Interference is the phenomena which is associated with the wave nature of light. Interference is a phenomena which is associated with the wave nature of light. The phenomena of modification of intensity of light obtained by the superposition of two or more beams of light is called interference. When two or more beams of light, when they superimpose over one over another, there exists it results in a pattern, and that pattern is called interference pattern. If the resultant intensity is 0, or if it is less than, we expect from the separate intensities, we have destructive interference, while if it is greater, we have constructive interference. So interference is of two types, constructive and destructive interference. So interference is a phenomena of modification of intensity of light obtained by the superposition of two or more beams of light. When two or more beams of light are superimposed, you get a modified intensity of light. And that resultant intensity, if it is 0 or less than we expect, then it is said to be destructive interference, and if it is greater, we have constructive interference. Then, understanding more about interference. I would like to emphasize more about interference before studying about interferometer. You understand more about interference. Anyone who has thrown stones into a flat, glassy pond or pool and watched what happened knows about interference. If you take a clear pond and if you have thrown a stone into that flat, glassy pond or a pool, you will know the interference. You will observe the interference. When the stones hit the water surface, they generate concentric waves that move from the source. Where the point where you throw the stone, that becomes the source, and you will observe concentric circles or concentric waves are generated. Which move away from the source, as shown in the figure. You have seen the figure there. The figure shows the interference, the concentric waves that are generated when a stone is thrown on the surface of a flat glassy pond or a pool. What happens? And where there are two or more of these concentric waves interfere with each other, this interference can result in a large wave, a smaller wave, or no wave. So when these two or more of the concentric waves, when they intersect, they interfere with each other. They will be interfering with each other. each other and result in a larger wave, a smaller wave, or no wave at all. The visible pattern occurring where the waves intersect is simply called as interference pattern. You observe a visible pattern. The pattern where you observe that pattern is called the interference pattern. So the principles of interference are simple to understand. They are very simple to understand. Two or more waves, when they interact, you add the heights of the separate waves together as they interact. And the resulting wave pattern is called interference pattern. You add the heights. You add the heights of the two waves and you observe a pattern, and that pattern is called interference pattern. That pattern is called what pattern? Interference pattern. So coming to the constructive interference. You have in the figure shown aside, you can see there are two waves. The two waves are superimposed. They are superimposed. There are two waves. They are added up together. They undergo constructive interference here. The result in constructive interference. The amplitude of the wave will increase. The total constructive interference happens when the peaks and the troughs of the two waves perfectly meet up. When added together, you construct a larger wave, the size of which is equal to the sum of the heights of the two waves at each point where they physically interact. So this type of interference is called constructive interference. When the two waves at their intersection points, when the two waves perfectly meet each other, when they get added up together, you get constructive larger wave, the size of which is equal to the sum of the heights or the depths of the two waves at each point where they are physically interacting. At each point where they are physically interacting. This type of interference is called constructive interference. This type of interference is called constructive interference. Then the next type of interference is the destructive interference. When we see the destructive interference, we have two waves here again. The two waves are not meeting. When they are not in phase. The two destructive interference occurs when the peaks of one or more wave meet and match the troughs of identical wave. The peak is meeting the trough of the identical wave. It is not meeting, the peak is not meeting the peak of the other wave, but it is meeting the trough of the other wave. Adding these together results in them cancelling each other. So the magnitudes or the amplitudes of the wave cancel each other, and such type of interference is called destructive interference, and you have a flat wave altogether. So the total interference occurs when the peaks of one or more waves meet and match the troughs of another identical wave. We have two identical waves having the same frequency and they are having the same frequency. The amplitude of the waves are same. When the amplitudes are same, when the crest of one wave is meeting the trough of another wave, when they are superimposed, cancelling of the wave takes place, and this type of interference is called destructive interference. They get destroyed. So that this type of interference is called destructive interference. This type of interference is called destructive interference. So coming to the types of waves, we have seen here already, we have learnt. We have seen two waves of different amplitudes that are in phase. When the amplitudes of the waves are different. Previously we have seen the waves having the same amplitude. When the same amplitude is used during constructive interference, the total constructive interference amplitude is twice the original waves. Whereas when it is a destructive interference, the amplitude of both the waves, when they are added together, it gets cancelled and you get a straight line. So let us take the case when the two waves of different amplitudes but they are in phase. So the figure shows A and B are the two waves. A and B are the two waves having different amplitudes. If the two rays are in the same phase, then the resulting intensity will be sum of the two intensities. So the magnitude of A wave plus the magnitude of B wave will be added together and you get a resultant wave R. The resultant wave R. If the two rays are out of phase, if they are in phase, you get a constructive interference. If they are out of phase, then the resulting intensity will be the difference of the two waves. It will be the difference of the two waves. Difference of the two waves. The resulting intensity will be difference of the two waves. If two rays having same amplitude are in phase, then the resultant will be twice that of the original wave and it results with a bright spot. It results with a bright spot. If their amplitudes are same, the two waves are added up together and you get twice the intensity of the original waves or original light, and you will be having a bright spot. It results in a bright spot. If two rays having same amplitude, they are out of phase. When they are not in phase but they are out of phase, then the resultant will be 0, because the two waves are of same amplitude but they are out of phase. So the resultant will be 0. The resultant intensity of the two waves when summed up together, it will be 0 and the result will be a dark spot. When they are undergoing constructive interference, you will be getting a bright spot. When they are undergoing destructive interference, you will be getting a dark spot. You will be getting a dark spot. So this is the concept of interference. This is the concept of interference. So interferometers are used to study the fine structure of spectral lines to determine wavelength of monochromatic light. They are used to study the fine structure of spectral lines. They are used to study the fine structure of spectral lines to determine the wavelength of the monochromatic light. Basic principle: interferometers make use of the principle of superposition to combine waves in a way that will cause the resultant of the combination to have some meaningful property that is diagnostic of the original state of the wave. So you get some useful information when they undergo constructive interference. Some useful information is being extracted from them. So they have the meaningful property that is diagnostic of the original state of the wave. That is diagnostic of the original state of the wave. So this is the principle of interferometry. Interferometry is widely known as an important investigation tool or a technique. As I told you, it is used for investigation, for finding out some unknown quantity. So it is known as an investigation technique based on the superimposing of two or more wavelengths of same frequency. You should remember the frequency is same. Two or more wavelengths of same frequency when they are superimposed. While one light beam interacts with the object being measured and the other does not, and their constructive interference results in a pattern or spatial shape that can then be used for extremely accurate and complex measurements. So you get a pattern, interference pattern. From that pattern you can analyze the substances by using that pattern. That pattern can be used for extremely accurate and complex measurements. You get a very accurate and complex measurements can be carried out using the interference pattern. Coming to the types of interferometers. There are several types of interferometers used today in the modern day. We have the first and the foremost is the Michelson interferometer. Then Fabry-Perot interferometer, fringe counting interferometer, NPL flatness interferometer, Pitter NPL interferometer, Zeiss gaze block interferometer, multiple beam interferometer, and laser interferometer. These are the 8 types of interferometers that are used. Most commonly, seen type of interferometers: Michelson's interferometer, Fabry-Perot interferometer, fringe counting interferometer, NPL flatness interferometer, Pitter NPL interferometer, Jesus gaze block interferometer, multiple beam interferometer, and laser interferometer. These are the different types of interferometers that are available. Among which we are going to study about Michelson's interferometer. Components of interferometer. What are the components or the parts of the interferometer? The interferometer consists of a source which gives monochromatic light. It consists of a source which gives monochromatic light. Then you have the collimating lens for making the light ray, monochromatic light parallel, to be made parallel, rendered parallel. You want a parallel beam of light, you use a collimating lens. Then a transparent glass plates we use. Then we have mirrors and telescope. So these are the 5 components of an interferometer, or 5 parts of an interferometer are source which gives monochromatic light. Then we have collimating lens to make your light radiation parallel. You need a parallel beam of rays to fall on the transparent glass plates. Then we have the mirrors and the telescope. These are the 5 components of an interferometer. 5 components of an interferometer. So this is the basic structure of your basic diagram or optical diagram of your interferometer. So you have the source, as I told you, the source is a you have a light source of monochromatic radiation. It emits monochromatic radiation. Then the next stage is the collimating lens, which makes the radiation falling on it to give you a parallel beam of rays. These beam of rays, they strike the 2 transparent glass plates. These are the 2. There are 2 transparent glass plates, and we have the mirrors. 2 mirrors are there, and the telescope. So this is the basic structure of your interferometer. The working of your interferometer. The light from the source is monochromatic light which strikes the collimating lens. The light from the source is monochromatic light which strikes the collimating lens. The collimating lens converts the light into parallel beam, and this beam falls on the transparent glass plate. So the light from the source is a monochromatic light which strikes the collimating lens. The collimating lens converts the light into parallel beam, and this beam falls on the transparent glass plate. The rays get refracted by some amount by the first transparent glass plate, and they fall on the second transparent glass plate. The rays, they get refracted by some amount by the first transparent glass plate, and they fall on the second transparent glass plate. Here the rays get refracted by still further amount and finally strikes the mirror M1. These rays are called refracted rays. So the light ray coming from the collimating lens, it gets refracted by some amount by the first transparent glass plate. After refraction, again it is made to pass and made to fall on a second transparent glass plate, where it is furthermore refracted, and finally it reaches the mirror M1. This ray is called refracted ray. Some rays at the transparent glass plate gets reflected and reach the mirror M2. These rays are called reflected rays. Remember, some of the rays, all the rays do not pass through the mirror, through the first transparent glass plate and then go to the second. There are some rays which does not go to the second transparent glass plate, but they are reflected back and they reach the mirror M2. These rays are called reflected rays. The reflected rays gets reflected by the mirror M1, and reaches the transparent glass plate 2 and refracts the rays by the same amount. Also, the mirror M2 reflects the reflected ray onto the transparent glass plate 1 and finally gets refracted by the transparent glass plate 1 by the same amount and reaches the same point C, where it forms an interference fringe pattern. Okay. So, the rays from the collimating lens, they fall on the, I'll just show you the figure once again so that you can understand much clearly. When seeing the interferometer here, the source is emitting the monochromatic radiation. So, when the monochromatic radiation strikes the collimating lens will generate parallel beam of rays. These beam of rays, they fall on the first transparent glass plate. The rays get refracted by some amount by the first transparent glass plate and falls on the second transparent glass plate. Okay. Here the rays get refracted by still further amount and finally they reach the mirror M1. This ray is called refracted ray. You can see in the figure it is mentioned as refracted ray. Okay. Then some rays at the first, when we take the first transparent glass plate, some rays, they get reflected back and reach the mirror N2, and those rays are called reflected rays. The refracted rays, where are the refracted rays? They are reaching the mirror M2. So the refracted rays get reflected by the mirror M1 and reaches the transparent glass plate 2 and refracts the ray by the same amount. As initial, how they got refracted, they will return back by the same amount. Also, the mirror M2 reflects the reflected ray on the transparent glass plate 1 and finally gets refracted by the transparent glass plate by the same amount and reaches the same point C. So, it reaches the same point where the two rays interfere. One is the refracted rays and the reflected rays. Both they interfere at the point C, where it forms a pattern called interference fringe pattern. It forms a pattern called interference fringe pattern. Interference fringe pattern. So this is the working of your interferometer. I will like to explain the interference, how the interference is taking place. This is a figure which shows there are two slits R1 and R2. The light coming from R1, it is falling on the screen. We will see it in clearly. The measurement of how you are going to measure the refractive index of the substance that is placed in the path of the ray. The measurement of refractive index is based upon, as interferometers are used to measure the refractive index of materials or substances. How you can use this meter to measure the refractive index? The measurement of refractive index is based upon the interference of light. The light enters and leaves the solution at right angles. Parallel light passes through the original opening R1 and R2. Since R1O and R2O are equal length, the two beams arrive at O in phase and a bright spot results. Once again, you see here how you are going to measure the refractive index. I am going to explain here using the interferometer. The light enters and leaves the solution at right angles. Parallel light passes through there are two openings, R1 and R2 are the two openings. So the light enters the meter through the openings R1 and R2. Since R10, R1O and R2O are of equal lengths, they are of equal lengths. The two beams arrive at a point O in phase. As I told you, when they are in phase, you have a constructive interference and a bright spot appears. Okay, it appears on the screen there. If a substance of slightly greater refractive index is placed at C. Now first what you are doing, you are not using any substance, just you are using air, and you are allowing the light to pass through the two holes, and the light ray, it falls at a point O from both the openings R1 and R2. As the optical length is same, is equal, the two beams of light, they superimpose, they undergo constructive interference, and they form a bright spot at O. Now what you are doing in the second case, you are placing a sample or a material whose refractive index is to be determined at a point C. So the optical, now what happens when the light ray, monochromatic radiation of light, when it passes through both the openings R1 and R2, as usual R1O is as earlier it is. Now at R2, in the direction of R2, you are placing a substance whose refractive index is to be observed, is to be studied. Then now here, when the material is placed, the optical length of the beam R2O is increased by an amount of delta B, by a small amount of delta B, because the velocity of light through C is decreased. When it passes through the substance, what happens to the velocity? The velocity decreases. When a material is placed in the pathway, the velocity of light decreases. Hence, thereby it takes its intensity decreases. So the optical length of the beam is increased by an amount of delta B. By an amount of delta B. Okay. Hence the optical length is increased. Length is increased by an amount of delta B, because the velocity of light through C is decreased. So the expression for finding the refractive index of the sample, you have an expression for finding the refractive index of the sample is given by the magnitude of this increase depends upon the thickness of the sample. Magnitude of what? Magnitude of B. What is B? B is the optical, it is nothing but the length. It is the optical length. Optical length that has increased. So delta B is nothing but B into nu minus nu naught. So the thickness of the sample and the magnitude of this increase depends on the thickness of the sample and upon its refractive index. Sample and its refractive index, and is given by the relation delta B is equal to B into nu minus nu naught, where B is the thickness of the sample, nu is the refractive index of the sample, and nu naught is the refractive index of the medium. Initially it is air. Air's refractive index is 1. Okay. So this is how you are going to find out the refractive index of the sample. You know the thickness of the sample. You know the value of refractive index of air. You can calculate the value of the refractive index of the unknown sample. This is how this interferometer is used to determine the refractive index of substances. So the magnitude of this, as when the sample of thickness B is placed in the pathway, what happens? When two beams of rays are made to impose at a point, before introducing the sample, they undergo constructive interference. After introducing the sample, the thickness, because of the thickness of the material or the substance placed in the pathway, what is happening? That because of the thickness of the sample, the refractive index of the sample, because of the refractive index or the thickness of the sample, the velocity of the light beam is decreasing. When the velocity decreases because there is an increase in the length of the amount optical length. Because of increase in the optical length, as the light beam has to pass through the sample, there is an increase in the optical length by an amount delta B, and because of that the light intensity is decreasing. Light velocity is decreasing. So delta B is equal to B into nu minus nu naught, where B is the thickness of the sample, nu is the refractive index of the sample, and nu naught is the refractive index of the medium. Then coming to the relationship between interference with refractive index, the velocity of light in two media are proportional to their indices of refraction. You should remember that velocity of light depends upon the refractive index of the media. The two beams no longer arrive in phase at all. Earlier, when there was no sample in between, the two beams they interfered, they were in phase and they met at the point O. But now in the second case, you are placing a substance of sample of thickness B, and this sample, when you are placing that sample, now no longer the beams are in constructive interference, but at the other point O, which is now optically equally distant from R1 and R2. Okay, the two beams no longer arrive in phase at O, but at some other point O dash. Okay, they will be reaching some other. I will show you once again. See, the two beams now what they are doing. Earlier they met at the point O, but now when the sample was placed, they are going to meet at another point O dash. They are going to meet at another point O dash. Another point O dash, which is now optically equal distance from R1 and R2. The entire band of the system will be shifted by this amount. From O to O dash it is being shifted. So thus, with substance at C in the path of one of the beams, by counting the number of bands which the central band has shifted, we can determine the value of B into eta minus nu minus nu naught. We can find out this value by now counting the number of bands. You are going to count the number of bands. Number of bands are called fringes, in other words. If two plates of, let's see the construction and working of an interferometer. If two plates of equal thickness were placed in the two beams, the number of bands that the central band shift would be a mean of calculating the refractive index of one of the plates, provided the value of the other one was known. You should know the refractive index of one of the material. When two materials are used, one should be known, another one will be unknown. The optical length of the two beams is equalized by means of a glass plate in the path of each beam, P1 and P2, at an angle of about 45 degrees to the beam. One plate being fixed and other attached to a lever by which it can be rotated, thus increasing or decreasing the effective thickness. The movement is measured by a micrometer screw. This is turned until the central achromatic band of the two systems corresponds. Until the achromatic band of the two systems correspond. So, for light, the expression for finding out the number of fringe patterns, that is the band, we call it as number of fringe patterns. For light of wavelength lambda, the distance between O and O dash measured in number of fringes n, each made up of dark and light bands, is given by n is equal to delta beta by lambda, or n is equal to B into nu minus nu naught by lambda, where lambda is the wavelength of light, n is the number of fringe patterns, B into eta minus eta no, nu minus nu naught, B is into nu minus nu naught. You know nu naught, the refractive index of the medium, nu will be the refractive index of the material, B is the thickness of the sample. By counting the number of fringe patterns, you know the wavelength, you can find out the refractive index of the material nu. You can find out the refractive index of the material nu. So this is how we are going to find the refractive index of any unknown substance by using interferometer. This is the Michelson's interferometer. We have the light source, we have the two flat mirrors, then we have beam splitter, two flat mirrors placed at right angles to each other, flat mirror 1 and flat mirror 2 and 3. Then we have the beam splitter in between, and we have your observer or the eyepiece, the telescope, where through it containing the eyepiece, where the person can observe. He can observe the fringe pattern. When they constructively interfere, you can observe the fringe pattern. Okay, this is your Michelson's interferometer. So a Michelson's interferometer is a tool. It is a tool to produce interference between two beams of light. Michelson's interferometer is a tool which is used to produce interference between two beams of light. Two beams of light. It is the most common design for optical interferometry and was invented by Albert Abraham Michelson. That's why it was named after the scientist Albert Abraham Michelson as Michelson's interferometer. Michelson's interferometer produces interference fringes. They produce interference fringes by splitting they produce interference fringes by splitting a beam of monochromatic light such that one beam hits a fixed mirror and other hits a movable mirror. When the reflected beams are combined, an interference pattern is observed. An interference pattern is observed. To create interference fringes on a detector, the path have to be of different lengths or composed of different materials. Michelson's interferometers are relatively simple in operation and possess the largest field of view for a specified wavelength. They also possess a relatively low temperature sensitivity. They have low temperature sensitivity. So Michelson's interferometers are relatively simple in operation and they possess large field of view for specified wavelengths. For large field of view for specified wavelength. Coming to the applications of interferometers. Interferometers are used to measure the quantity of methane and carbon dioxide in air. They are used to determine the permeability of balloon fabrics to hydrogen and helium. Permeability of the balloon fabrics, the balloons, material with which the balloons are made, that their permeability can be determined using interferometers. They are used to determine potassium and sodium in a mixture of their sulfates and chlorides. Then they are used to measure carbon dioxide in blood. They are used to measure carbon dioxide in blood, ethyl alcohol. Okay, they are used to measure carbon dioxide in blood, ethyl alcohol in blood, concentration of heavy water. The wavelength is used for detection of optical beam precisely. Wavelength is used for detection of optical beam precisely. Widely used in dense wavelength division multiplexing. They are widely used in dense wavelength multiplexing. And in astronomical interferometry, they find widespread applications in astronomical interferometry also. Astronomical interferometry. Okay. And they are often used to make very small measurements which are not otherwise possible in other ways. Very small measurements can be made much more precisely. They are powerful for detecting gravitational waves. They are powerful for detecting gravitational waves. That is one of the advantage of these interferometers. In the field of fiber optics, interferometers are employed. In the field of fiber optics, interferometers are employed in the precise measurement of small displacement, refractive index changes, surface irregularities and topography, among other observational procedures. Okay, they are used in the field of fiber optics. Within the field of fiber optics, they are employed in the precise measurement of small displacements, refractive index changes, surface irregularities and topography, among other observational procedures. And as I told you, in space industry, interferometers are used by astronomers to obtain the resolution of large telescopes by combining the signal from multiple smaller telescopes that act as a single unit. Okay, in astronomy they are used. Okay, so these are the application areas where interferometers are most widely used. Interferometers are most widely used. To summarize our topic of discussion today, we have understood the concept of interference. We have understood the concept of interference. What is interference? Interference is a phenomena which is associated with wave nature of light. The phenomena of modification of intensity of light obtained by superimposition of two or more beams of light is called interference. It is a phenomena which is associated with wave nature of light. And that phenomena of modification of intensity of light obtained by superimposition of two or more beams of light is called interference. We have two types of interference, that is constructive interference and destructive interference. If the resultant intensity is 0 or less than what we have expected for separate intensities, we have destructive interference. If it is greater than what we have, it is called constructive interference. It is called constructive interference. When two waves, they are separately, when the two waves interfere, when the peak and the troughs of the two waves meet up together, and when they are added together, you construct a larger wave, the size of which is equal to sum of the two waves at each point where they are physically interacting. That type of waves are called constructive interference. That type of interference is called constructive interference. In destructive interference occurs when the peaks and the troughs of one wave meet and match the trough of another wave. When the peak of one wave meet and match the trough of another wave, adding together results in cancelling of each of the two waves. That type of interference is called destructive interference. So if two rays are in same phase, then resulting intensity will be sum of the two intensities. If they are out of phase, the difference of the two will be the resulting intensity. If the two waves have same amplitude and are in same phase, then resulting intensity will be twice, and the result will be a bright spot observed. And when we have, if two rays having same amplitude are out of phase, then the resultant will be 0 and the result will be dark spot. You will be observing a dark spot. So what is the principle of interferometer? Interferometer makes use of the principle of superposition of two waves that combine together in a way that will cause the result of their combination to have some meaningful property. That is diagnostic of the original state of the waves. That is the basic principle of interferometer. There are several types of interferometers. Michelson's interferometer, Fabry-Perot interferometer, fringe counting interferometer, NPL flatness interferometers, Pitter NPL interferometers, Zeiss gauge block interferometers, multi-beam interferometers, and laser interferometers. Coming to the components of an interferometer, we have the source, which is giving monochromatic light, collimating lens for collimating the beam of light, transparent glass plates, then mirror and telescope. So the working principle of an Michelson's interferometer is the light from the source is monochromatic light which strikes the collimating lens. The collimating lens converts the light into parallel beam, and this beam falls on the second transparent glass plate. Here the ray gets refracted by still further amount and finally strikes the mirror M1. This ray is called the refracted ray. When the sum of the ray that at the first transparent glass plate gets reflected and reaches the mirror M2. These rays are called reflected rays, and the refracted rays get reflected by the mirror M1 and reaches the transparent glass plate 2 and refracts the ray by the same amount. Also, the mirror M2 reflects the reflected ray onto the transparent glass plate 1 and finally gets refracted by the transparent glass plate by the same amount and reaches the same point C where it forms an interference fringe pattern. Suppose you are placing a sample in the path of the ray, you can find out the refractive index by knowing the thickness of the sample, and delta B is equal to B into nu minus nu naught, where B is the thickness of the sample, nu is the refractive index of the sample, and nu naught is the refractive index of the media in air. Then the fringe patterns are given by the formula n is equal to B into nu minus nu naught by lambda. Lambda is the wavelength of the light, n is the number of fringes that are being observed, B is the thickness of the sample, nu is the refractive index of the unknown sample, and nu naught is the refractive index of the known sample. So Michelson's interferometer is most widely used for this application, for widely used interferometer, use it for investigation of components. So applications of interferometers are, they are used to measure the quantity of methane and carbon dioxide in air, they are used to determine the permeability of balloon fabrics, they are used to determine the potassium and sodium in a mixture of their sulfates and chlorides. They are used to measure carbon dioxide in blood, and the wavelength is used for determination of optical beam, widely used in dense wavelength division multiplexing, and in the field of astronomy, they are most widely used in the field of astronomy. Interferometers are used in the field of astronomy, and in the within the field of fiber optics, interferometers are employed in precise measurement of small displacement, refractive index changes, surface irregularities, and topographies, among other observational procedures. In the space industry, interferometry is used by astronomers to obtain the resolution of large telescopes by combining the signals from multiple smaller telescopes that act as single unit. A complex system of mirrors brings the light from the spectral telescopes, separate telescopes, to the astronomical instruments. Okay, so these are the application areas where the interferometer meters are used. So with this, I would like to end my presentation on interferometers.